So today we will discuss on heterogeneous catalyst design, addressing deactivation and scalability issues. That is the title. So in this, first we will talk about what is heterogeneous catalysis and how it is relevant to nano chemistry and nanoscience, which most of you will be interested in. Is what I was thinking. And then we'll talk about deactivation. So that is a kind of a new topic I may be introducing to master's students or even early research students. So I'll talk about why it is important and what it is and what to look out for, and how we have done some design addressing this deactivation. And finally, if time permits, I will just touch upon some of the scalability issues. So what is scale in heterogeneous catalyst, because this is a very application oriented research field. It is the most industrialized area of research in this domain. So how scale affects the catalysis, and how as early researchers you can actually start incorporating those thoughts into your work and understand how it will be translated later. So that is how I will do the lecture. So I will, in this slide, I will kind of connect the heterogeneous catalysis and its on nanotechnology and its relevance to heterogeneous catalysis, the other way around. Yeah. So I don't have to talk about nanoscience. I think I'm probably it is part of a standard curriculum right now. So everybody knows what is nano, and then these kind of images, pictures, probably thousands of that you may have already seen. But when you think about, I'm assuming that you're all chemists or physicists in masters and early research, right? So when you think of nanoscience and all that, what comes to your mind is mainly quantum dots, this photoluminescence, optical and optoelectronic properties of such nanoparticles. So this is a range, size range you are talking about, right? And this is a quite a new, in one way new area of research. The famous, talk about their space at the bottom and all that kind of things, right? So you are talking about one around sub-nanometer to around 25 nanometer is where that optical and optoelectronic properties will be. And it is the same range where heterogeneous catalysis works. In the same range, sub-nanometer particles to around 25 nanometers, it will be 10 to 25 nanometers is where heterogeneous catalysis also works. But that has been there for a long time. This is a paper from 1925 by Hughes Taylor. He says that the surface of a granule may thus be regarded as composed of atoms in varied degrees of saturation by neighboring metal atoms. So he understood that time that there is some difference on the surface of the thing. He's talking about small particles, and 1925. And actually, he was talking about, he's a practitioner of hydrogenation of various chemicals, and that started by Sabatier. You all must be knowing about Sabatier process, where CO2 hydrogenation was discovered. That is in 1880s, late 1880s, he may have done that. And that is when hydrogenation became very important, and people started looking at it in an industrial scale. Some of the first industrial scale processes started using this hydrogenation, right? So this is Wilhelm Norman in 1902 patented this vegetable oil to saturated fat. So basically margarine, lard, in our case, dalda. I don't know, you people may not know, but you may remember dalda, the existence of dalda in our life. For a long time in my childhood, I thought dalda is oil, an Arctic oil. That's what I thought. I did not even realize that it was a company name. So that is dalda. It is nothing but hydrogenate vegetable oil, make it into vanaspati ghee, butter, because butter and ghee and all became very expensive and not affordable. So this became industrial process, instead of having a cow and making 1 liter of that every day, you make 100 tons of it every day. So it became industrial. That is how that industrialization happened in vegetable oil hydrogenation. So that is when they realized, and Sabatier had already realized that nickel is very good hydrogenation catalyst, right? So same catalyst was used in vegetable oil hydrogenation also. So that is, you look at that particle, right? It's the same. It is the same region of nanoparticle which you are otherwise aware of. So I would say that heterogeneous catalysis is the oldest form of nanotechnology. without ruffling too many feathers around. So that is a thing. Even though they did not call it nano, but they realized that there's something unique about the surfaces of nano metals, especially when the particle size reduces, right? Yeah. So we'll go a little bit. I will just take a few seconds to get a historical perspective on that. So that is one part in which the nickel catalysis was growing, and people were trying to understand how this is happening. So from 1920s onwards, we have a lot of papers which they're trying to understand how we can improve the selectivity, how the quality of the final vanaspati can be improved, and all that. And parallelly, we were having a petroleum industry also coming up. So that started in the late 1800s by oil production. So this is you can actually search in the Google for this. This is a Kiers. I couldn't make it bigger. So it is a fellow named Kier. This is an advertisement pamphlet of this Kier trying to sell off rock oil. He's calling it rock oil as a medicinal medicine. Actually, he's telling it is wonderful properties it has for your skin and for your stomach. So I can't imagine what poor people went through when they drank that for their stomach problems. Maybe, I don't know, maybe he claimed that it can lead your take care of, sort out your ulcer problems and all that. So that kind of a thing. So they were like, they got this, they did not know what exactly to do. So then they realized that whatever it is floating, he has written there, 400 feet I dug for salt water, and then this is floating on the surface, it's a magical liquid. And that liquid, they realized that it caught fire, right? So they realized that it is a very good lighting oil for that. But when they burned it, it didn't burn very, crude oil, you can imagine like a thick thing, it didn't burn very nicely. So they started refining it. In that process, and some catalysis, I wouldn't say, distillation and all those kind of like large scale processes started. This is one of the first wells of Kier. And in 1900s, then this automobile started, right? Automobile, initially they started with methanol as a fuel, and we are now 100 years later, we are going back to methanol, right? But anyway, so then they realized that this oil, if it is cleaned up, it burns even better than methanol. So they started cleaning, and that is when a whole petroleum industry kick-started it in a huge level. The scale was like huge because the automobile production also started like kicked off, because the assembly line started. Industrialization happened very fast. So in a couple of decades, everybody had a car. Not here, probably in US or something. And then catalytic cracking started in 1937 using platinum on alumina catalyst. It's a very, very simple catalyst. We'll talk about that. So you can see that, right? So there's a simple alumina in hundreds of nanometers to micrometer alumina particles. On that, you have this around 7 to 10 nanometer particles of platinum. So in 1937, they started using it. They did not know, okay, nano is just good and all that. They just, by serendipity, they got it, trial and error, they started using this. And parallelly, in non-petrochemical regime, Haber process was developed in 1905. And we now think that Haber process was useful for fertilizers and all that, but they started it for explosive synthesis, not for fertilizer. We should not think that all these are very benign and useful things. They started it for explosive, and that is why, because of its destructive nature, it got so much of market, and then it is iron oxide catalyst, Haber-Bosch process. When it became Haber-Bosch process, it became an industrialized. And in 1970s, again, polymer industry started, and then it just went in another direction, right? Everything. Now, I think if you look at any material, from our false ceiling to the slipper we are wearing to whatever I'm holding here, everything has gone through, everything is from fossil. Nothing, I mean, we can't claim to be any renewable or anything in any of this. Everything is from fossil. And all of it went through at least one heterogeneous catalyst, if not 10 catalysts to get to this stage. So everything has gone through it. So that is the prevalence, all prevailing area of research now. And right now we are using it in all these things. See, nothing has happened to Haber-Bosch. It is the same catalyst, same company, everything is same. Petroleum refining, everything is the same. Same catalyst we are using. Even now, platinum alumina only we are using, and iron oxide only we are using for Haber process. And now all these are happening. Along with, we need to now address all the pollution problems which are happening, CO2 emission, now how to take care of the CO2. So that some of you may be working on that. So CO2 mitigation, all that is becoming very important now. Because of all these processes, we are creating CO2 and we are addressing the CO2 again. So all that is there, and green chemistry, renewables, net zero is something which you may be hearing a lot now, how to recycle. So you produce CO2, but you recycle CO2 into a fuel. So that whole thing becomes a net zero process. So all these things are being now done, but using mainly heterogeneous catalysts. So that is the importance I just wanted to show you. So we'll just go through quickly some of this catalysts which are used traditionally in the industry. So platinum on alumina, as I said, petroleum refining, and nickel on alumina, like we saw, hydrogenation, and also something much more important right now is hydrogen production. So all the industrial scale hydrogen is produced from methane through something called steam reforming of methane. So that process, catalyst is always nickel on alumina, and Haber, and sulfuric acid, PET and all that, vanadium oxide based catalyst. And I will not touch zeolites in this talk. And another thing is catalytic converter. Like I said, net zero and pollution abating and all that. Catalytic converter is all the cars you are driving right now have catalytic converters. It's nothing but platinum on alumina only, actually, but with a much more engineered and designed. So that is what, as time progressed, it's the same. My postdoc boss used to say that periodic table is that only. You're not going to change that. But now you have to design better catalysts with the same 5 elements which are available to you. You have to design the same. They were working in this catalyst with Johnson Matthey. So that is it. So the layering of platinum and barium and alumina, that was more important there, and that is how it works. And COMO, NEMO, we call that. This is for desulfurization and all. Desulfurization is very important for us right now because the Bharat 6 and Bharat 4 and all that, you may have heard of the diesel and petrol stages. So there you have to bring your fuel sulfur content to 3 ppm. 10 ppm, like that, very small, very low levels of sulfur is. Otherwise, sulfur will form sulfur oxides and then acid rain, and all the other issues with that. And then another thing is methanol synthesis. Again, a large scale, like 10,000 tons per day is like an average production of a plant. So that kind of thing. But if you look at all these things, when I write platinum/alumina or nickel/alumina, it means that platinum particles are deposited on the oxide. So that is what it means. And we in general call these type of materials supported metal catalysts. So this is nothing but nanoparticles of the active metal. Nanoparticles of active metal and nanoclusters or anything, like I said, sub-nanometer to 25 nanometer also can be used as catalyst. Will be deployed on supports. So most of the supports are usually oxides. Normally we use oxides, but there are some cases in which sulfides are used, especially in sulfur-based catalysis. Sulfides are used, carbides are used in new methods. They are being used, but they are not in an industrial scale. It is not there. And in a catalyst, supported metal catalyst, for example, I showed this earlier. This is platinum and this alumina. Most active sites are usually metal nanoparticles, usually. But support material can be inert. In all these cases, it will be inert. But alumina, if you have any, in solid state chemistry or something you have studied, alumina can exist in multiple phases and with multiple surface characteristics. It can be basic, it can be inert, it can be neutral, it can be acid. From pseudobromide to alpha alumina, beta alumina, all kinds of things are there. So based on all that, this support material can take part or not take part, depending on the catalyst and all that. So, but most of the time it is a metal particle which is the most active, and which is something which we need to design for better activity. And there is something called metal support interfaces. I won't have much time to deal with this, but I will just quickly talk about this metal support interfaces. That is one of the ways in which you can control the deactivation of the material also. So we'll talk about some of these things. So now going to the nanoparticle or the metal thing. So first, before even going to the nanoparticles, we'll look at some of the shapes. So maybe this is very, very rudimentary for you people, but I'll just quickly go through it so that you will register it faster. So some of the Platonic geometries and also related geometries I've just given here. So you start with the cube, you cut the corners, you get an octahedron. You start with the tetrahedron, you keep on cutting, you go through a square pyramid and then again to a tetrahedron. Then you dodecahedron, icosahedron. This is T icosa, I think. So these are the shapes which are normally available in nanoparticle regime as well as in crystal things. So if you look at some of the like sodium chloride, it will mostly it will come as a cube. So like that, it's a crystal. It is depending on the crystal chemistry also. So if you look at this, now you assume that when it forms a nanoparticle, if I have a nanoparticle of cubic shape, then what is it actually? It is a shape which is getting filled with atoms. So it's as simple as that. So I will take it a very simple thing. So this is how it will be. So I just fill up that cube with a thing, and this is, if you look at the side, this is how it will be. So I'm assuming that you all know crystallography, some crystallography, Miller indices, how to arrive at the Miller indices and all that. So in a cube, if the face you are looking at is 0, 0, 1. You cut it like across like this, it becomes 0, 1, 1, 0. And then you cut across that whole diagonal, it is 1, 1, 1. It is like that. So this is how the atoms will be placed in the nanoparticles also. And of course, nature always prefers minimum energy and stable structures, and always a close packed. This is a more close packed. You can look at that. No, if you look at this is more close packed than the others. So it always prefers. So that is why most of the time you look at the nanoparticle, it will be like spherical thing, but it's not spherical. It's more or less like this. So we'll look at how some of these things form. So if I take a cube, this is a cube, right? You can understand that it's a cube. I'm just looking down the 1, 1, 1. And if I keep on removing, that orange is that one single atom at the corner of a cube, 1, 1, 1 atom. Now I keep on removing that, right? Yeah. So I have more 1, 1, 1 exposed. So I'm having a more and more 1, 1, 1 close packed planes exposed. So that it becomes a cube octahedron, that's certain. Then it becomes truncated cube octahedron. And finally, this is how it will look like. So these, from cube octahedron to cubes to truncated cube octahedron, these are all nanoparticle shapes which are normally present in the in nature. I mean, nature in the sense when we synthesize also. So now how do we synthesize that? How does this transform, right? If you let this 1, 1, 1 plane grow, it becomes completely, you keep on removing, it becomes an octahedron. So now you have a shape where all the faces exposed are close packed, all 1, 1, 1. And if you look at this, if you let this one grow, it grows back into the cube form. So here it is all 0, 0, 1, right? The least goes back. So this is the crux of the, it's a crux of the nanoparticle synthesis. Like you have fantastic structures, such precise control right now. After 100 years of this, people can really do. You can synthesize. I mean, I think Pradeep probably has synthesized in such controlled manner, thinking like, okay, 1, 1, 1 plane is what you want in 25 atoms. This is what you have to do. So that kind of precise control is possible right now. And this is how a cube octahedron, which I showed, will look like. You will have lot of things. So when I said let something grow, how you will do that? When in the synthesis, you protect the other thing. For example, some protecting agent you use to protect the 0, 0, 1 planes, right? So only 1, 1, 1 will grow. So it is like that. So all said and done, you will have all the surfaces will be having protecting agents. So all these will be completely occupied with all, some ligands or something. And most of the time, people use sulfur ligands because of the affinity, high affinity of sulfur to all the metals. So because of that, it is actually not the best thing for catalysis, because you can understand that the active sites are metal sites. And if you cannot access that, because it's already having a sulfur long chain atom molecule sticking onto that, then it is difficult. So because of that, all these advances made in optical and optoelectronic property related field of nano science and nanotechnology is not directly translated into heterogeneous catalysis. Even though that is exactly what we want, we are not able to translate it directly onto it because of the this active site blockage by the protecting agents and all that. It's not a stable. You all may be aware that nanoparticle shapes and sizes are not very stable. The surfaces are not very stable. So any harsh conditions, they may agglomerate and all that. We will talk about that. And again, it is a homogeneous phase. So it will be difficult, and then it is difficult to do a 10-ton synthesis. So because of that, we need to have these materials supported on very stable surfaces. So that is where the heterogeneous catalysis starts. So now we'll have a little very schematic, very simple way of explanation only. So this is a typical heterogeneous catalysis. So I took one of those this nanoparticle and I just put it on oxide surface. So this orange is nanoparticle and this blue is the support. You just assume that. And I'm not saying that any this is inert. Some silica or alumina, it is completely inert, and this is only active. And this, you can see that now you have lot of edges and all that. So I'm not even looking at that. In a simple sense, what happens? So we'll take two examples of CO oxidation and cinnamaldehyde hydrogenation, right? Simple examples. We'll talk about this more later. So look at CO oxidation. So what is CO oxidation? It is CO, oxygen. They should come and attach onto the surface. I'll just quickly they will come, adsorb, have a transition state, and then form CO2 and dissolve. So that is a simple animation schematic. And this is what. So you have the CO, adsorbed CO and oxygen, which reduces. So in reaction, when you think about reaction in a simple way, two molecules, two reactants collide and form a transition state, which transition state will reduce the activation energy, and that is how the reaction goes. But in this case, what happens? It is not that molecules collide. Molecules really have a adsorption state with the catalyst. So that is how the activation barrier is reduced. So this is how it is. So it starts with here, and then CO and oxygen, which is adsorbed, it reduces the energy barrier, and that is how the catalysis happens in the case of heterogeneous catalyst. Now, there are different ways of CO. CO can adsorb onto a surface through carbon, through oxygen. So depending on the metal, depending on what you want, all that can be designed. And another thing is, here also I'm not right now looking at which plane and all that. We will come to that later. But look at cinnamaldehyde hydrogenation. Now cinnamaldehyde is a big molecule, right? So it has many different modes of adsorption. For example, it can adsorb through C and O onto two different metals, or through the C double bond C bond to one metal, or that it can go and stick onto the surface like this. So it just goes and stands on the surface like this, so everything gets. So, and each of these products, depending on that, each of these products form. So for example, if it's CC, this gets hydrogenated. If it is CO, this gets hydrogenated. If both are there, this forms. And if this also gets hydrogenated, it is a fully hydrogenated product. Even this ring also gets hydrogenated. Ring hydrogenation happens. So this is how this hydrogenation. It's a simple reaction, but that is how it happens. And people have really tried to understand which plane, which mode of adsorption is better for the which product. So those kind of things. So this is the reason why heterogeneous. I think one more mode of this is what I wanted to say. If it is through here, then this gets hydrogenated. If it is like this, then any of those things get hydrogenated, or all will get hydrogenated. So people have tried to understand why this is happening, why a certain mode of adsorption is preferred, and which is a minimum energy, in adsorption mode in all these things. So we can kind of understand why this is happening. So now we will look at the particle size effect on all these things, right? So why this is important is that because the particle size is a very unstable, parameter. So it can change very drastically with conditions, temperature, pressure and all that. So that is why it becomes. So there are three different ways. One is like as particle size increases, it drastically reduces. And another method is, another mode is when there's an optimum thing. Most of the reactions fall under this. There's an optimum reaction because electronic effects also form. And then another thing is like it is not at all dependent on particle size after certain sizes. So cinnamaldehyde hydrogenation is like that. It is other way around. It doesn't really care about the particles. It's independent. Bigger particle size is better. So like that, particle. But all these things are for particles which are above 1 nanometer. And now you may have also heard about single atom catalysis. So this is another very, very new, maybe 10 years, 15 years old thing. So people were able to just put one single atom onto the support instead of having a nanoparticle or a nanocluster. So that is like sub-nanometer and one atom. So single atom, and in this paper we will explain in the next slide. So you have single atom plus atomic catalyst. They say like 1 or 2 atoms come together, it is an atomic catalyst, and nanoclusters and nanoparticles. So in 2025, after 1925, we are still working on like how the particle size effect is affecting the simple. This is just a platinum on alumina or silica catalyst. So that is what I wanted to. So let us look at it. It's a platinum on silica catalyst which they are trying. So you can see the particle. I can't see from here. You can see the differences. So this is single atom. This is single atom is just one single atom, and single atom plus atomic catalyst is around 0.5 nanometer, and then single atom plus nanocatalyst is nanocluster is around 1, like that. So there is a distribution. So they could make it in very, very precise manner, so that we will understand the effect of this. And they did just CO adsorption, CO oxidation only. And you will think that single atom catalyst will be the best, right? We are told that, like more and more atoms are available for the reaction, better things. So that is why we keep on reducing the particle size, thinking that surface area to volume ratio is what is more important. So you bring it down to single atom, it will be the most active. But actually, it's the other way around. Single atom catalyst is the least active in here. As the particle size increases, it becomes more active. So that is why it is not merely particle size effect. It's not surface area to volume ratio effect. It is actually a lot of electronic effects also become. So why this happens here is weaker CO adsorption on platinum single atom. So they did lot of DFT studies, of course, with the computational power increasing. So I think that is why you will probably. So I think with the increase in computational capabilities right now, and with the AI on quantum computing and all that, my computation colleagues are on the moon now. They are like, okay, we can now sort out all kinds of problems. So they have understood using DFT that CO adsorption on platinum single atom is weaker than platinum nanocluster and nanoparticles. So that is the reason why this is happening. And oxygen dissociation energy is lower in nanoclusters. So it's all depending on electronic effects also. That is why, and that is because there's a stronger electron transfer from nanocluster nanoparticles to reactants. That will lower the energy barrier of transition state, which I mentioned earlier. So that is why we need to understand that it is not just a surface area to volume ratio, which is what we usually talk about in heterogeneous catalysts, that you reduce a particle size, everything is going to be okay because your surface area is more. But it's not just that, because a lot of electronic effects also come into play in this regime. We are talking about 20 nanometer and 50 nanometer, maybe not much difference, but you're talking about 20 and 1 and 7 nanometer, that's a huge difference in electronic properties. So these are things which I'm not very good at. So I will just expose you to that so that you can read about it. But this is electronic effects due to particle size. Anyway, we had worked a lot on this gold nanoparticle, so we could understand a little bit on that. So as the particle size decreases, quantum confinement effects also come into play, and then it becomes a molecule. This is cluster, right? Cluster becomes molecule-like. So that is the electronic effect actually you see when you are bringing the particle size down. And this is something which you all can look at. Professor Jens Nosko. This is all the heterogeneous catalyst practitioners usually look at his papers, because he has got a D-band alignment theory, correlation theory, or alignment theory. So what he suggests is that if you look at the metal particle, the active metal particle, and your reactant molecule, if there is a D-band alignment of your metal particle, then your adsorption properties are better. So that is how, and then there is things called volcano plot, M plot, and all that. And so we try to understand which alloy will work better, things like that. So this is one of the first papers in 1997, where he just took the platinum D-band center and correlated to different sites. So he just took a normal particle, and then it has like different like if you take even a cube octahedron, like I said, or cube for that matter, that single atom at the corner is 111, right? So like that, they made different they calculated, it is not experimental, they calculated for different planes, different atoms in the corners, kings, surface, sides, lot of names are there for that. And then he correlated this to coordination numbers. So yeah, so this is what it finally some of the results which came out, and you can see that they are all quite recent papers where they could prove, because experimental conditions and spectroscopy methods became very advanced. So you can now see it. So if you look at the cubo-octahedral shape which I showed, which is the most prevalent, your coordination number increases as particle size increases, right? So same in the cubic also. So coordination number increases with particles. So one of the reasons why lower coordination numbers are better, lower particle size is better, is because of the coordination number. So that is why maybe the single atom is not very relevant. It is a coordination number of a particular atom. And if you remember that first slide which I showed, 1925 paper of Hughes Taylor, what did he say? That there are atoms which are not fully saturated. So he thinks that something is happening. So this paper is from I think next paper probably is from 2025. In that, they have realized that actually the coordination number is the most important thing. So that is what they have done here. So this is they made a surface of platinum 111. This is experimental. Platinum 111, coordination number 9. It is like a simple thing. It is not active for CO oxidation at all. It doesn't adsorb CO, nothing happens. But they just etched the surface and made triangular clusters on 111 with a coordination number of 7. All these red things are all coordination number 7. Same plane, nothing happened. They just etched that thing out, and that became highly active. So that red thing, it's a coordination number. It's a plane is not different, but the coordination number is different. So they could experimentally prove also that coordination number, if the control of coordination number is what actually matters, right? So these are also going back to Noskov's theory, metal atoms are expected to exhibit stronger interaction with adsorbates because of higher energy D bands. So that D band correlation also is happening with the lower coordination, with the coordination numbers. So now, with all these very basic things which probably you were all aware of, but I wanted to just conclude and put everything in perspective by saying that what are the vital parameters in heterogeneous catalysis we look at, because then we can move into deactivation. Yeah. So one is adsorption. You know that the whole heterogeneous catalysis works under the premise of molecules adsorbing on the surface close enough so that they can react and form a transition state which will reduce the energy barrier, and then react and desorption. So adsorption, desorption, both are important. It should not be that adsorption is weak and desorption is very strong, so that the molecule doesn't come out. That means that you have to go to very higher, harsher conditions to desorb that. So everything should be in an optimum thing. And characteristics of surfaces. So that becomes important. You saw that it is not simply the surface area exposed. It's also electronic effects and D-band alignment. All those things also come into play. And adsorption, desorption energies of the molecules, which is notwithstanding all this. So what is the most important when you're looking at metal supported particle catalyst is particle size and shape. It's the most vital, and it through interactions of atoms in various planes and things like that, which you saw. And finally, it all boils down to coordination numbers. So that is why shape also becomes important. And And now you can understand. So I have very like those people have made it etched catalyst, which is very fantastic. You put it in a vacuum chamber and do your reaction. But then the moment that thing changes, your reaction may happen at 200 degree, and your etched surface may not be stable at that, because these are high energy surfaces. They will come together, they will change, they will under reaction. People are now observing under reaction what is happening. So those kind of things happen. And when that happens, and now because your catalysis was depending on it, the moment you change anything around the electronic property through size and shape, your effect is negative and it becomes deactivated. So that is a problem.
When you talk about the aging of the nanoparticle, the shape, so if we think logically like that atoms with the coordination number 7, that exists there itself. So aging is really needed. Like
it is there, but that is why, because of the coordination effect. Or now it has some coordinately unsaturated sites for it to react. So that is the most important thing. It is the same plane. It is there only, but it was coordinated to another 2-3 of its neighbors. But now that is not there. So that then it becomes literally that. Okay, did I change? No, yeah. So now we will look at deactivation. Now how these things are changing. So deactivation means that it was active. Let us say 90% conversion was in CO oxidation itself is a very simple reaction. And when the activity comes down or selectivity comes down, for example, CO2 hydrogenation I am doing to methane and CO. So it was active for methane, it was not active for CO, but then some changes happen and CO started producing, like that. So selectivity and activity, when that changes for the worse, it is called deactivation. So some of the mechanisms is, one is sintering or agglomeration of active metal clusters, nanoparticles, etc. And since they can be under thermal or even hydrothermal. So you have a little bit of steam in most of the industrial processes. There will be some steam, because to prevent coking, which we will come to later. So under hydrothermal conditions, also these particles can change their shape and size. And poisoning of active sites by impurities. For example, sulfur. You all know that most of the nanoparticles are made with protecting agents, right? So that is because those things have better affinity towards the surface, and that is a problem in industry, because you have in fossil fuel, any crude oil you take, there will be sulfur in it. Even biomass related, even natural materials have more sulfur in it because of the proteins and stuff like that. So everything will have sulfur. So sulfur has a more affinity towards metal. So because of that, these things will go and get stuck on the surface and activity reduces. So that is one thing. And another thing is a permanent deposition of carbonaceous material. For example, some reactions are spontaneous and it doesn't really need a lot of energy. And coking is one of that. Hydrocarbons, you take any hydrocarbons, especially in petrochemical industry, you will have methane to God knows, like 36 carbon atom. That is the way the raw material which they deal with. So that will crack, and all the hydrogen will go, and all this carbon will just form aromatization. It's called aromatization, and then we just stick on the thing. So that is called coking. So this is also one of the important deactivation mechanisms. So here it's an interesting picture I've shown here. So if you see here, this is a platinum and alumina, industrial platinum and alumina catalyst. Okay, after a few hours of very harsh treatment, I think it's at 800 or something, they have just heated under hydrogen. This is what happens. So you can see that platinum is literally under microscope. They could see this platinum moving literally. So you can see it started with this. This is how controlled it was. You can see that here, right? How controlled the particles were, and that became this. So literally it is a migration effect. So I will explain that using a scheme. Yeah. So now if you see, now I'm just having a scheme where I'm taking. It is not going to be extremely homogeneous. Like you will have 5 nanometer particle, 10 nanometer particle, but overall the error will be quite minimum in good catalyst. But like I will take a big particle and then a few small particles, and this is a very, very nano cluster, like atomic catalyst, I will say, so 3 atoms are sitting there. We can't even see properly. So now you see that what happens when I heat it. So when I heat, all the small particles will come towards the big particle. Literally, the big particle will attract. So that is called Oswald ripening. So it is through migration and coalescence. So particles can just come together, and if there's a bigger particle, so once it starts agglomerating and forming big particles, it will just keep on eating like a big hole. It just take on from all sides, and then finally, what happens is that those small atomic clusters are there, right? So they just go through some phenomenon called vapor transport. Vapor phase transport. So that also just literally becomes vapor. It's not a migration because it is an atom catalyst, no? So atom particle. So it will have much better interaction with the support. So it may not really move, but it will vaporize and become part of the big particle. So that is how it happened. That is what you saw earlier also, how certain planes, things were just moving and coming together and forming like 100 nanometer particles. So, and this is very much visible in some of the gold catalysis. So even fresh catalyst, you can see that it's a highly active, and then it just small, and then under different conditions, just not very high temperatures. It's 200 degree only, but still it is how it is coming down from 45% to around 5% within 45 hours. And another thing which was very surprising for a lot of people working in gold catalysis was it did not have a shelf life. You just make the catalyst. I don't know how many of you face these things if you're working in gold catalysis. You just make the catalyst and then keep it even in very nice, like in the fridge, packed well, everything. Still, you look at the under air, nitrogen and vacuum they have kept and how it is coming down. So shelf life of the catalyst itself is very poor. So that means it really doesn't need many things for all this agglomeration, deactivation and things of that sort. Where am I? I should put that. Oh. Okay. So that is what we thought of addressing. So now you look at the conventional catalyst. This is how it is. Like you have a support, which is like a 2-dimensional support. You can consider looking at the particle size. It's a huge, like 1 micron particle. On that small, like 10 nanometer particles are sitting. So I consider it as a 2-dimensional support. And then these things can move together, like migration, coalescence and all that, which I showed earlier. And what we thought is, like, let us now reduce the freedom of movement of these things, just kind of like encapsulate them. So first we encapsulated them in a like 1-dimensional channels of SBA15. I think you may have heard of the mesoporous channels and all that. So we put that in channels of this sort. And then also we realized at very high temperatures like 800, 700, the channels are also not very stable. And again, agglomeration is happening, not as severe as the conventional, but still it is happening. So we thought, okay, it's better than to completely encapsulate it. So 0 dimension of movement. So here I've written from 2-dimensional movement to 1 dimension to it cannot move. It has to stay there because it's completely covered with oxides or the support. So this I will.
Close, a little bit closer.
Oh, you said. Oh, okay. But okay. Anyway, I will. Somebody asked.
That agglomerations can be prevented by addition of some emulsifying or suspending agent. Because,
yeah, but then that is for protecting agents. They will be, they will go and sit on surface of the catalyst, right?
They are forming agglomeration due to some interactions.
Yes.
So what I'm thinking, addition of some emulsifying or suspending agent, they will not interact with each other. They will repel each other.
Yeah, they will repel each other, but they'll be covered with that, right? With the protecting agents. Then when I'm doing your the catalysis, they may not have that kind of access to the surface. That is why nanoparticles are stable, right? People are making nanoparticles which are stable. But the problem is that then catalysis may not happen. Activity may be less. Yeah, so we selected SBA15, which is like a channel, 1-dimensional channels of silica, and that is made using polymers of like polyethylene oxide, polypropylene oxide, and that forms based on the hydrophobicity, hydrophilicity variation of these two block copolymers. So we thought, okay, let us put the metal precursor inside. If you just take the SBA15 or any support, and just normally we use methods called impregnation methods, wet impregnation, dry impregnation. So you just add the precursor and dry it, and then calcine it so that and reduce it. So that's a simple procedures. So if we do that, then we realize that these particles are going and getting deployed all over the surface. So we wanted to avoid that. We wanted the particles to be exactly inside the channels only, not outside. So we just put that along with the template. So this template is what forms these structures. So we put it there. Then we realized that because of the hydrophilicity, all this is going and sitting in the middle and forming big particles. So, and then it is not really forming the material, the channel itself. So we then added a C-tab. We thought, okay, C-tab has a positive thing, so some kind of electronic interactions will be there, and then it will come out nicely. And this is how we proceeded, and that kind of like worked out. And if you look at here, you can see that it is monodispersed, like 8 nanometer plus or minus 0.001 nanometer variation only, very small variation. Very highly monodispersed particles could be seen inside the channels. And at 0.7 weight%, so cinnamaldehyde hydrogenation I showed, right? So the 8 nanometer particles are very good for cinnamaldehyde hydrogenation. So normally when you have to make it big particles, you need to use more precursors. So your weight percentage increases. You need to use more matter, so that more noble metal, so that your particle size becomes bigger. But here we could get the same conversions with just 0.7 weight% of platinum. So you are reducing the noble metal usage a lot. So that is something which we could do. And then how now to control the particle size. So particle size, then now because of this, it is not going to move, and then we could do reactions at 500 degree without much of problems. So you can see that, then we kind of like played around with it, and from particles we could go to rugby ball shaped particles, just by varying the time of diffusion within the template, and even this. So usually again to make these nano rods, you need to have something like 40%, 40 weight% of platinum you literally force into the channels and make those nanoparticles. But we could do it within 1 weight%. In 1 weight% itself, these things could form. That anyway, I think if you are interested, you can just see this chemistry of materials paper. There we did lot of diffusion NMR to understand how that particles are diffusing through that. Because of the diffusion effect, we could get the shape morphology. And also we could change by changing the template characteristic, template size variation, we could go from 8 nanometer to 5 nanometer to 2 nanometer. Like that, we could get very good control of particle size. So this is the effect of particle size. We studied again CO oxidation, the simplest reaction. So we have used that, and we also could realize all this was made in one-dimensional channels of different sizes. So 2 nanometer particle was quite good yield, but as the particle size increases, it doesn't really matter. Then it is all similar actually, 0.1 and 0.15, not much difference. So that huge variation happens at a particular. So I showed you how particle size effect varies in the initial thing, 3 mechanisms. So this is one of those mechanisms. And again, like I said, we just played around and made many different things. So here then we realized that this is that platinum SB15 which I showed, till 500 it is quite stable, no variations. But at 750 you can see how it is. It is literally breaking the walls of the channels itself. So another thing is there that that channel itself, silica itself, is not very stable at that temperature. Maybe because of that also, that particle size increases a lot. So, and this is also reported by other groups, that at 400 degree, how the from SBA15 particles kind of like break out. So what we thought, let us go for full encapsulation. Now it is like one dimensional channel is there, so fully encapsulate. So then lot of reports are there, lot of good work in the last 2010s, lot of good work about this. So but most of these things were focused on photonics again, like how to stabilize your photo properties, photoelectric and optoelectronic properties of gold nanoparticles through encapsulation. So that was the aim of all this work. But for us, it is not possible, because in this kind of encapsulation, it is completely covered. You see here, like you have the particle and then it's completely covered. Again, the same problem. Now, how will the reactant molecule, for example, CO and oxygen, how will they reach the gold or platinum, right? So that is another problem. So we thought, okay, let us we need to go for a shell is thick, it's okay, but it should be porous. So we need to make that, you need to encapsulate, but make that encapsulation porous. Then things can go inside, and it will have a gate effect also, which will enhance the stability of the catalyst. So that is what we did. And some papers were also already reported. But you see here, if you normally when you take clusters, you have a hydrophobic interaction in water, so all of them will come together, and then finally when you encapsulate, state of the art at that point of time when we started was this. So you can see that it has a shell, but multiple things are there in a core shell kind of a thing. So that is not going to, again, it is not meant for catalysis. It's not going to survive the catalysis conditions which I will be using. So what we did was to make water dispersible ultra small metal clusters. So we thought, okay, let us start with very small clusters. Even if it moves around a little, if I start with 1.5, I can end up with 3. 3 is good enough for my catalysis. So that is the aim, and we made some specific ligands to do this, and so that individually each cluster, it will have multiple clusters, but individually each of them will be encapsulated and not in a core shell model. So that is what we did, and we could really get so it has very nice gold. Then we got into this fluorescence, and it started glowing very nicely. It was very, very interesting times. And then we did it, and this is what we got. So you can see that, right? So these are the particles. These are the gold clusters which are encapsulated. It is 1.5 to 1.7 nanometer, and we make this by after calcination at around 350 degree. So 350, this is what we got. And then anyway, I will not do this. And then in gold, we could see some a little bit of agglomeration. Like instead of 3 nanometer, we ended up with 5 nanometer when you start heating it to 500 degree and all that. But 5 nanometer is okay. It's not, but it was not as stable as what we thought. But in the case of palladium ultra small clusters, you can see here, right? 350, it's around 3.2 nanometer, and 550, quite stable, no issues. At 750, it just went to 3.5 nanometer average. So we could nicely encapsulate it with highly porous, oxide. So, and we did quite a lot of reactions. I don't want to go in the details of all these things. And we went, again, if you get something, you just kind of like play around with it. So gold, and then gold palladium, because gold palladium is quite interesting, because the problem with gold palladium is that when you normally make this alloy by thermal treatment. So when you thermally treat, usually particle size increases. So there is no control of particle size, but if you want to have a good control of gold and palladium concentration. So that is what people were facing. So, but we could really do that. We could get reasonable control of gold and palladium concentration, because it's encapsulated, and thermally it was getting treated, but it was not increasing the size so much. So at 750 also we could control the particle size. So it is, you should also think that it is gold we are talking about. Gold is not at all stable. Shelf life. Shelf life is bad for this catalyst. But if you encapsulate it like this, shelf life, or not shelf life, even thermal stability becomes very interestingly increased. And then silver, again, silver is also another one metal which is very, very prone to deactivation through all kinds of thermal degradations. That also we could do. I think I will skip this also. So this is something, another poisoning. So now you saw that the deactivation through thermal instability, right? The agglomeration, sintering and all that can be avoided by, I wouldn't call it avoiding, I will say minimize using encapsulation as a method. And it's not just us, there are other groups also have worked on this, and reverse micellar method and all those kind of things. You can look up those things. And another thing is, second point which I talked about is sulfur poisoning in general, with anything outside the reactant stability comes and attaches onto that, which has more affinity towards a metal surface. So that is the thing. And what we did was, now palladium on silica we have, right? So we wanted it to be sulfur tolerant. So palladium is notorious, any noble metal is notorious for sulfur affinity. They are not very good under H2S and all that. So this is as in the sense. So what we thought is, like, if you have, anyway we have pores, right? And we have this thing, this encapsulated oxide on surface. So you put something there which will react with your H2S and will not allow that H2S to come in, but only the CO will come in. So we wanted a gate which will close when H2S comes, but open when CO comes. So that is like, so it's like a gate kind of a thing we wanted to make. So we know that H2S desulfurization, cobalt is a very good desulfurization catalyst. So it reacts and it forms some other sulfates and all that, and which can be regenerated. So what we thought is, we just deployed some cobalt onto that. Different methods we have used. We have used APS, selenization, and then cobalt anchoring and all that. So whatever it is, we put some cobalt on the top of the thing. So nothing much has happened. It's very small weight percentage of thing, and particle size also is reasonable. And you look at this, then we can see that cobalt is on the surface of the silica, and palladium also we can see. But we haven't published it yet, because I mean, I'm not convinced where the cobalt is. So, but I cannot really honestly say that, okay, it is there on surface, or it is really on the palladium. So I'm not very convinced, or haven't published, but I just wanted to say that this is one method. So if you guys have any better way of understanding this, or better way of making it, it will be a very nice thing, this gated kind of methods. Okay. So this is the results we have. So you look at this, that this is a palladium silica. So we under this is C oxidation. So C oxidation, light off happens. It's called light off. It just goes up. So light off happens, and then at that point we pass H2S, and then you can see the deactivation. It just comes down to zero. Literally, it just deactivates. It's a very well-known phenomenon. But in the cobalt palladium, and the same conditions, you see how it is. Light off, and then maybe 3% reduction. That could be based on anything. So that is what. So no effect at all on the C oxidation. So we think that this is a very good way of doing, and then we could do, and then sulfur XPS also shows that sulfate is forming. So we could see that some kind of a sulfur interaction on the surface is happening. And then of course this can be taken up to base metals. Copper again, for example, copper catalysts are again notorious for getting affected by chlorine. Any halogens, bromine and all that. So that also we could prevent by doing the encapsulation. And another thing I talked about is hydrothermal stability. So hydrothermal stability of the oxide can be improved, because you remember that when the SBA15 itself, when you heat it, it is not very stable after certain temperatures. So, but that can be improved by adding heterogeneous heteroatoms. For example, silica means you can add aluminum into the thing. So that improves the oxide stability, not the particle stability. So that also we could do post-synthesis. So now coming to support metal interaction. So I talked about we talked about the metal particle. Now you remember that we also talked about the interaction of the support. So that is something which I will just quickly go through. So now you see, this is a gold Syria. These are all time resolved HRTM images, aberration corrected. So gold Syria, if you take, this is time, okay. So from 0 to it is just going the time. So you can see that there are 4 particles and how these 2 particles are moving and forming this big one, right? So that is exactly with the coalescence I was talking about, right? So this is what happens. But you see that on Syria, which is a reducible, substrate, reducible. You know that cerium can be in Ce3 plus, Ce4 plus, and multiple. So it is reducible, but it is very stable. It can move back and forth very easily. So that is why it's a reducible. It's a much better support. And the same catalyst under silica, you see how it is. Still, I can see the 3 particles, and the particle size also has not become too bad. But if you look at this on silica, now I have 5 particles. At the end of 120 seconds after this, I have 2 very big particles, much bigger than the ones which I started. And another thing which is very, very important, I think it may have struck you, that look at the shape of the particle here and here, right? So this is like a hemispheric, like it's just sitting like this. That means it's like imagine a water droplet on a hydrophilic surface. It wets it, right? If it's a hydrophobic surface, it goes and forms a drop. That is exactly what happens on silica. So that in 2022, so experimentally it is proved that the wettability of the metal on the support is what makes that support interaction. So that is, it's a strong metal support interaction, which we have been talking about for a long time. We knew that, but absolutely, like in front of your eyes, you are seeing that is this very recent. And this is the strong interaction of gold and ceria is through bonding, oxygen vacancy, and polarization. All this is because of the metallophilic contact of gold and ceria. So this is also something which people can work on. Even though a little bit of idea we have, like for example, reducible oxides are better and the interaction is better, so that it will not coalesce and move around and all that. That is important. And another thing which they here they studied, but I didn't put that whole, it was fully on DFT, is because so this is a one particular plane they have used, and the atoms at corners, you were asking that why is that corner. So in that corner, so what they are saying is that this particle is stable because it is at the corner of that. So there's more interaction between that cerium atom and the gold atom. So those kind of things also people are.
So this wettability is a solid state, right? I mean,
Solid state. Its wettability is not the right term, but it is like a metal wettability or whatever.
Spreads or not?
Spreads or not, yes. So that is very important, is what we have understood now. So now the final thing is coke formation, carbon formation. So any industry process, industrially important process you take, like I said, most of it has gone is from fossil fuels, and all are crude from crude oil. So you start with the long chain, and very, very branched, hydrocarbon. That is where your starting material. From there only all the rest of the thing is formed. So when that is there in any of your material, from C46 to C1, methane is it's notorious. I work a lot with methane. You can't even do an in situ experiment using XRD using methane, because the heating element of the XRD chamber is nickel based. So nickel is a catalyst, and this methane will go and crack on that. So it is that notorious, it just cracks on everything. And my students actually suffer by cleaning the reactors, because we do large scale experiments. So it's a mess. So this is like my enemy, I hate them. So anyway, it's an interesting problem though. So there are multiple places where this carbon can form. It can form on the metal. So like I said, nickel, it can just form on the metal. And if the metal is on the surface, it may not really affect your reaction. You will still leave with some 70-80% of the conversion, and then you are happy, no problem. And on support also it can form, because some of the supports, like acidic supports, like alumina, like I told, alumina can be from inert to acidic to basic, whatever. Acidic and basic supports can also crack hydrocarbons. And metal particle encapsulation. So if it is a big particle and then you have enough small carbon particles, it may be active. But if it is in a small pore of the support and it's completely covered with the thing, again it is a problem. And another major issue is this carbon viscous. It is carbon viscous. So it is like carbon nanotubes. You all know CNTs, right? How are they made? By cracking methane or any other hydrocarbons. People use acetylene and all those kind of things also. So it is just you have like literally single atoms of iron in it, iron in the flow through some precursors, and then that single atom, this carbon nanotube grows. So if the conditions are correct, if your pressure, concentration, temperature, everything is correct, this forms. This also is like it's quite bad. Look at that. How, and another thing is that it breaks the particles. So it is called dusting. So if you have a, let us say, your very nice active 20 nanometer particle is there, you made with great difficulty, you made a 20 nanometer particle. This forms and breaks that into some 1 nanometer and completely cover it. So these kind of nasty things, this carbon does. And mainly it is through decomposition of hydrocarbons. Another one thing called Woodward reaction. This is even nastier because it doesn't need any catalyst. It can form anywhere you want, like in the reactor, in the top of the reactor, the bottom of the reactor, in the GC line, everywhere this Woodward carbon will form because of the concentration of CO. For example, I work on dry reforming, which I will come to. It has very high concentration of CO in the reactant. So after the reaction, Woodward will form, and polymerization of unsaturated compounds. So this is also important. Actually, we want aromatization. That is one of the major industrially important reaction itself, aromatization. So we need, you start from ethylene and form benzene. So that kind of a thing, but instead of just forming benzene, what it will do it will form like an naphthalene and, like indines and things like that, highly networked, aromatics. So those are the problems. So some prevalent, right now what people are doing, oh, I don't have time. Okay, I will just quickly, I'll finish now. So what you can do is alloying. Like I said, nickel is notorious for it. But what you can do is, you can do alloying so that your carbon formation is reduced. But it will compromise the reaction which you want, your desired reaction, which could be any of the reforming, for example. That can be. And also addition of steam or oxygen doses. So what happens is, carbon forms, but immediately the carbon gets gasified into, if it is oxygen, it goes as CO2. But if you put steam, then it can form hydrogen also, which is anyway good. But the problem is that hydrogen will again reduce it and then increase the particle size, and it just goes on. And intermittent regeneration. This is what mostly industrial catalysts. So industrial catalysts, when they come itself, it comes with a lifetime. So they will say, okay, 5 years. So in 5 years, maybe 3 times you need to completely shut down, regenerate. So when the carbon forms again, you completely shut down the reaction, and then you start oxidation, you remove all the catalyst and all that kind of thing. So intermittent regeneration is what people normally do. It is nothing to do with the catalyst design, but you can also design catalyst based on that. So I'll quickly do that. So what we have done is, so again, I'll go back to the simple scheme where the nanoparticle cluster was there and support was there. And now we know the nanoparticle is active. So, but I don't mind little bit compromise on the activity if I can incorporate that as ionic sites onto stable lattices. So that is what we have been doing for long years, and we could develop a lot of catalysts which are highly stable under very drastic conditions, because these oxides are quite stable. So that is what we have selected, like all kinds of catalysts, and perovskites work very well because of the stability and the window of doping, and that is what we do. Active metal incorporation, it prevents sintering. So there's no, because it is in the site and the energy of that is very high, it is not going to move around. And optimize suppose sites, like for example basic sites and all that, I can use the rest of the compound to do that. And we could really improve that a lot, and I will just not I'll go through all these things. So this is one example where we could really control the coke formation by introducing cerium doping into the pyrochlore which we did. So you can see that this is a catalyst, and all the rest of it you can see that filamentous carbon and all that forming. So you look at the carbon formation, this optimum cerium is the minimum. So this is what we think. Because of the introduction of cerium, oxygen vacancies are formed, and that oxygen vacancies will regenerate and form gasification sites on the surface of the catalyst. So this is one way of designing your catalyst, looking at how to bring more hydroxyls, vacancies, all that into the catalyst. It doesn't have to be compounds like perovskites and pyrochlores and all that. You can do that on just normal oxides also, how to bring in those things, and look at the stability. So that is, with that I can stop, or I can just take 2 minutes more. Okay. Yeah. So I just wanted to, because you're all starting your research career, I wanted to just talk about scale in catalysis. So when you are doing something in the lab, you should also keep in mind that your aim should be this. So this is where you start. You do some 50 ml reactor with a catalyst amount of 500 milligram, but your aim is this, right? 10 to 14 meter length of tubes. And just recently I visited an industry where 288 such tubes are used for producing hydrogen through SRM. So that is a scale which is so nobody can do that scale in the lab. But when you are working on it, you can think that, okay, from here I need to go to a different scale. So your design of the catalyst can be based on that knowledge. Because one of the common things people, I will just skip this, common things people are now working on is photocatalysis, right? It's very much researched in India especially. So when we are doing that, we always forget that when we use a powder catalyst, maybe very active, you will be using some 1 microliter reactor, small reactor, and then use a laser and then do the reaction. Perfect, no problem. But you also try to see how you can scale that up. Is it scalable in the first place? So we did some reaction just to understand that. So just this is one of the best catalysts from literature we have taken. Very good catalyst, very high efficiency and all that. And it is very high, it increases drastically. But after an optimum thing, you see how as we keep on increasing the thing, it comes down because of scattering. So that scattering is a major effect in photocatalysis. So that is something which you all can, if any of you are planning to work on photocatalysis, can think of how to reduce the scattering. So it is not a very scalable thing if you just use a powder catalyst. So these are the things which we try to reduce that effect using internal reflection phenomenon by using optical fibers. We just coated the catalyst on the optical fibers and did the thing. So we could really scale it up. We just increase the number of fibers. So it was not really affecting the final thing. So this is what I wanted to expose you to the question of scale. So when we are talking about very small, your catalyst may be very good, but how does it get affected by increasing in the scale? That is something which you can do. You can do yourself and understand. Okay? Yeah, that's.
Ma'am, how do you design the catalyst to avoid metal leaching or sintering in the harsh conditions?
Yeah, so one method is encapsulation, which I talked about, right? So you encapsulate, then you think that it is not going to move around, the collisions and Oswald ripening does not happen, and then you will be able to control it. And we could control it, like even gold, palladium and all that, you saw that it could be controlled around 3 to 4 nanometer. One method. The other method which we used is lattice incorporation. So lattice incorporation, but you need stable, some lattices, like we usually use perovskite, pyrochlores, anything stable and easy to make. We don't want very fancy synthesis methods. So, and then dope the atoms. But there you can also try to, there's some design aspects in there, because you need to know the doping happens, whether there will be a, this doped elements will come out under conditions. Those things you need to look at.
How do you use computational like DFT and microkinetic?
I don't. No, I don't. I collaborate with people who do that. Yeah, I don't.
You use the term light off when you
Yeah.
are explaining the H2S. So I didn't understand that.
No, that is.
So why you are introducing that H2S.
No, no, no.
70% of CO.
No, so the thing is, the light off is when usually oxidation reactions happen as a light off, because it has it will not be active, and suddenly the activation barrier is broken, and then your activity increases. So that is called light off. It is because it's a hockey stick and all that kind of thing. That increase is there, no? So that is where we passed H2S to deactivate it.
So that is, we can say, activation at that point.
It is activated. It's activated. It's supposed to be a highly active, and then we pass H2S, and if it's not with cobalt, it just comes down. But if it is with cobalt, it stays.
Thank you, ma'am, for gracefully revealing the inner story of heterogeneous catalyst designing. Thank you.